how they help with Yarn and distributed in general. Let me start with the broad trend that's driving continuous problems. So the notion of computer itself is evolving from a single node to a large set of nodes in a data center. And with the model of computer being a data center, it also needs operating systems to go with it. And there's a number of courses, like Yarn itself is kind of acting as an operating system for this data center computer. They associate another effort, and more recently, just a couple weeks ago, Google announced this project called Kubernetes, which is again a nice way to manage the distributed resources in the form of computers. So if you think about how these operating systems and the version of this evolved almost 30, 40 years ago, the notion of processes and threads is very central to the operating system. It might be possible to build an application and run it directly on the hardware, but that would be very restrictive, and it won't. So for these applications to build into an ecosystem, you need the concept of processes and threads. An equivalent of that for this emerging model of data center computer is essentially a kind of being the enabler of that diverse application ecosystem that is being built on top of these data center computers. So what exactly are computers, right? So computer is actually a virtual abstraction of the underlying operating system. So the keyword here is actually abstraction. There's no substantial state associated with these containers. And that allows these containers to be very scalable. They're very lightweight. You can run, in standard conditions, you can run thousands of them on individual hardware because there's no state associated with them. But they can still provide a very strong level of isolation. Because these are implemented natively in the operating system, they're lightweight and essentially the same control paths that enforce security in the operating system also apply to them. And there is something going around for a long time that we introduced that the concept of containers in Linux and all the different use cases that go with them back in 2002. In fact, the original work was done to do these other cool things that are possible in the checkpoint restore. You can capture the state of the running application on one node, and then you can use the state to restore the state of those applications in that transient state on a different node at a different time. You can leverage basically take a running application, open up one machine, another machine. You can record relay, you have a very standard this application closely following each other. So we run them and go down, the other continue for all hours, with many other use cases, and all the language upgrades. Basically, you upgrade an application, upgrade the kernel without having to take down the application. There's many use cases. The core changes that needed to be implemented in the kernel are introduced. They basically touch almost every subsystem of the kernel, the VM and the network. And these changes took a lot of planning for them to be integrated into the kernel. And as of just a couple months ago, the most recent namespace is the notion of virtualizing a particular subset of the operating system. The most recent namespace is the namespace that got into the kernel. And once containers are available natively in the kernel, we create an opportunity for companies like Docker and a whole slew of other companies in the ecosystem to basically take those primitives, apply them to different use cases where they make sense. So this question comes up a lot. Virtualization has been very successful. It has essentially introduced a really new paradigm of application management in the last several years. So why not just use virtual machines? So the problem here is these applications have round edges, hypervisors provide square holes, they don't quite match. You kind of need an intermediate patch layer of this guest operating system to make these applications work on hypervisors. Ultimately, you want to virtualize applications, because applications that users care about and applications are what need to be virtualized, but what hardware provides, the hypervisors provide, is hardware interface so you need this guest system. Whereas in the case of containers, the system call interface expected by the application is exactly what a container provides as well. So now this guest operating system is a lot of trouble. Just to take one example of application I/O, a simple event in the application, like a write system call, would have to go through all these dense layers of application stack before the I/O makes it to the host. First, the write gets loaded the guest file system, which will hand that data to the guest driver. The guest driver will have to there's a big context switch. It's not just a simple context switch. It's a VM exit. There's much more state associated with the context switch. That we can go to that, and then it goes to the virtual device. Virtual device does the emulation report for that, and then it answers the image format interpreter. There are many different formats to go to EMDA, ODA, whatever. And they all have their overhead that they impose on this event that is traversing on the stack. And then it goes to the whatever storage protocol is the most. Every case, the containers they say is native. The write system called native basically is on the host. So the problem with a guest OS is many. First of all, in the case of Yarn, for example, some of these tasks are short-lived. They might run per minute, and it might take as long as 30 seconds for the OS to boot up. So it's not quite tenable to use virtual machines as the container for these tasks. And then if you have a large cluster and all these VMs sprawling across the cluster, you would have to do the batch maintenance. Let's say there's a lot of burden. There's a lot of maintenance where you pay for licenses, of course. And because of, again, this operating system on the state, and the memory state, and the resources it consumes, they're not scalable. You can run maybe several or almost a dozen VMs on node, whereas the container system scales much more. If you have multiple VMs running the same host, they all kind of are using the same operating system. Perhaps they all have these states that are sitting with same data in them. There's a lot of VM virtual memory duplication happening. That needs to be addressed. So what's generally happening is, because of this basic misalignment between application and hardware, there are all these different problems. And then there are conferences dedicated to addressing those problems. For example, the VM image is an opaque black box. In order to see what is inside, we need to do semantic analysis. We kind of need to understand the format of these file systems. And then there are techniques on how to, for example, keep track of the contents of these images and then do incremental upgrade. There's a lot of so-called innovation that is essentially trying to fix this basic misalignment. The underlying network topologies, storage topologies, and control topologies have obfuscated the data that's kind of working in, and any image which happens at the application level, when it comes down to the hardware, it loses its identity. For example, a write to a particular file translates into a block access on the device. And there's very little you can do with that kind of information without the associated semantic content coming from the application. So there's not much opportunity to do these optimizations. So looking at this in Yarn perspective. So Yarn itself has long moved away from the MapReduce batch groups. It is basically a platform to run an ecosystem of diverse distributed applications. And for this transition to be successful, we need the right mechanism of isolation. Containers actually it solves a number of problems using a simple embedding solution. So one of the problems that comes up a lot is distributing software. We call required by these tasks, and this software dependencies need to exist on the cluster nodes. And when you have multiple applications all sharing the same cluster, they have these software dependencies that may complicate each other. And so you kind of need isolation not just at the performance level. Performance isolation can be done with C groups, so there's mechanisms that can do that. But then it needs to go beyond just the performance isolation. And then it can provide a more complete abstraction to do that. So we've done initially an integration distributing the lab. So the idea is essentially the node manager, when it spawns its tasks, it moves on those tasks within this container. In fact, those tasks are contained. And containers can come up in a matter of hundreds of milliseconds, so it is very easy to do that. And basically the isolation is provided on a job basis. If there are all the tasks of one particular job would be brought up based on a container image that is associated with that job. And those tasks will run in an isolated way with respect to other tasks running on those. So this will provide the isolation needed for the software dependencies and what you know of that as well. So I'm just going to go through the value essentially that integrating containers into your containers. So you get secure multi-tenancy, especially with the recent addition to the list of namespaces supported by containers, the user namespaces. The root inside the container is different from the root on the host, so that the task will have the liberty to do whatever it wants to do, but without impacting other containers running on the host or host itself. I have a slide there which talks a little bit more about that. So performance isolation is a standard feature that exists for a long time in the C groups. So you can actually tune what the resources get allocated to the container. This can be tuned on the fly as well. It's just a matter of tweaking some constants within the code, because ultimately containers know what applications they're doing. There's detailed resource accounting that is already given in the ground. It's just a matter of checking what resource you wish to enforce. So this can be done on the fly. So sometimes the jobs have skewed resource usage. Some of them could be idle instead, some could be CPU bound. And when a task is scheduled on a particular node, it might not utilize all the resources available on that node. A normal solution would be to run a different task which kind of staggers the resources available on the host, but then that is usually not possible because the other task might be from a different customer. And running these two tasks on the same hardware has security concerns, so that at least we don't do that. What container setting allows is it provides isolation required so that you can compose together CPU instance jobs and IO instance jobs on the same host. And basically these are distributed applications with instances which need to see a consistent environment. So if one of the tasks of this job needs MATLAB, and other instances of this application also needs the same version of MATLAB. And engineering this is not so easy if you have a large cluster. So you basically have to go to each node and then install the same version of the software. There's an divergence that can move in and start debugs, and there's a lot of issues associated with that. So basically what container setting provides is that there's a central repository of these container images. And you can start with a stateless pool of nodes, and you can bring up your job, and the needed software context is brought streamed to the node on the fly. And it's guaranteed to be consistent because it is brought up based on the same source. I kind of already talked about software dependencies and configuration isolation. And one other interesting feature is that, and this is provided by Docker, is it has this concept of Docker files. So if you need to deploy software to a virtual node, you can use Chef Docker, things like that. But the way Docker files are different from that model is that there is runtime overhead associated with this deployment. So any commands that you ever run as part of this deployment get run on the fly, on runtime. Whereas with these containers, the Docker file specifies those steps roughly in the same way a Chef deployment is specified, but then the product of building the Docker file is a container image. And all of this building happens offline. And you're not paying the overhead of doing this runtime configuration, and you need to actually do the deadline. The container image is already pre-built, it is sitting in the repository, just needs to be streamed. And you can now programmatically specify the software context in which these tasks will run. That's very powerful and provides a lot of flexibility. Again, rapid provisioning, you can create a cluster starting from a stateless pool of resources. And you don't have to worry about the base platform. So for example, you would run a web container on top of an Ubuntu host. So this is the UID, and this is kind of core for containers because until now, Docker did not have support for UID namespaces. What it meant was any user, like you may have to be root to run Docker. And when you create a container, even as a regular user, you automatically get root privileges on the host. So that was kind of a non-start for using Docker professionally. But with user namespaces, the privilege associated with the container inside the root is limited to the container itself. So you can have a container supervisor with scope limited to the container, and then there's a different scoping for the entire host, and the container root gets mapped to a regular user on host. So any processes that are running inside this container would run as this UID 100 regular user. So that's the core content I wanted to present. There's a number of references here. So we're doing this work kind of in coordination between these two communities, Hadoop community and Docker community. There's missing pieces there. Basically, we need to bring it together with right APIs that provide the right flow between these two components. Some of those GIAs are listed there. There's also some articles that we're writing and a keeping track of the work we're doing. I don't know how we're doing on time. If I have some more time, I can go into my backup slides.
Sure, you still have 5 minutes.
All right. So, this is a new feature we're building, but in the meantime, to provide a multi-tenant Hadoop as a service offering, we need a solution that works today. And basically, this is what we started with. Basically, each customer gets a completely dedicated set of resources. And this is awesomely secure, all good, except you cannot scale our business this way because there's a lot of resource wastage that's happening here. And the maintenance burden and all those issues that I already talked about. So just by virtue of running these customer workloads on top of containers, we give a lot of flexibility. So each of these rows here represents one node, and in this part, there's three containers per node. So what this allows is we have a stateless pool of underlying resources, and then we can deploy customer workloads on top of them based on the associated container images. And once we have these tasks coming inside containers, then we can act them densely. And if you look here, there's a together to the fewer nodes. And then the resources associated with these containers can also be tweaked. So all of these things we are able to do just by running these Hadoop services without any changes to Hadoop or without any changes to Docker. We can already run it and then we can get these values. And again, distributed computing storage, that's possible as well, just by virtue of running these tasks consistently. So what we might not be able to do is the global scheduling. If the Yarn resource manager is in charge of all the resources available in the cluster, then with a global view, we might be able to make more optimal scheduling decisions. Whereas if we run resource manager within a set of containers, then the purview of resources that the resource manager is looking at is small, so it's a problem kind of partition, so the overall global scheduling might not be optimal. But this is something that we're playing with internally, and this serves us as an intermediate stopgap before Docker containers and containers in general are properly integrated into Yarn. I think that's the slice I have. Questions?
Any questions, guys? I was wondering about the Docker images, how lightweight or heavy or because you said they are streamed on demand, right? So is there a penalty plus anything?
Right, yeah.
And without a
so first of all, these containers they don't have the operating system in them. Kernel as well as the standard disk format and all that is not there. And what is in a container image is really the files themselves. And the objects are also incremental in that. So only the system requests needed for that distribution are stored. And on first pass ASP, you do need to transfer those bits for the network, but once they're there, then Docker uses copy on write file system to track the levels.
Okay. I have another question. A more basic question. I didn't get the relationship between Docker and your normal VMs, like VMware. Are they in the same space or is it just a variation of that?
This is a completely different technology. This is a fundamentally different technology.
Okay.
So virtual machines expose hardware interface, containers expose operating system interface.
So you would run this inside of VM?
You could run inside of a VM, you could.
I have a question actually on comparison with the traditional virtualization. So one of the things actually traditional virtualization at ESS gives you the notion of preserving a CPU, preserving memory by different tiers. So we kind of slice off parts of the hardware. So that's such a thing exists for me. And can you reserve, for example, can you say that I have this container, I'm going to reserve about 10% CPU, 10% memory?
Yes, you can. Basically by setting the resource limits, and you can do this, and when you specify those limits, the kernel can play a lot of intelligent tricks to optimally reserve those resources. In the case of VMs, for example, if you say you're allocating 4 GB to this VM, those 4 GB are actually allocated and unavailable for other users. Whereas in the case of containers, kernel has a global view of what's happening, and it has infinite context about what is happening in these stages. And kernel is already very intelligent in how it treats these facilities. It's very judicious on how things allocate, and it applies all those operations here as well. But it still ensures that those pages are available to you instead of those.
One of the things actually which often we do in virtual environments, there are private VLANs between, for example, independent VMs. Is there anything that can work?
Yeah, so we have integrated these containers with OpenVSwitch to provide isolation at the network traffic level. So you can basically that's our Hadoop. Essentially, a container can have its own set of network devices, its routing table, its own IP tables. So it's essentially an instance of an open system tree. So anything that OpenVSwitch does will also play the Linux, and that works perfectly fine.
Any more questions? Anyone from the back?
I just have a quick question on sharing of the containers. Like, so I can spin it up on my Mac and share it to the cloud. Is there any limitations to sharing containers across the web?
So, well, the container is a runtime abstraction, and then the image associated with it is the state. And there is a central repository of container images that Docker provides. You can also run a private registry or this repository occasionally as well. And there are very nice tools that are built to basically capture the changes you made to your container, and then basically do Docker push, and it uploads those changes to the registry, and can be pulled by somebody else.
Any other questions? One more here.
Is it possible to dynamically change the size of containers in terms of, let's say, memory or number of cores or any of these resources?
Yeah. Well, these are just resource accounting metrics maintained by the kernel. So it's just a matter of updating them. But support for it within Docker doesn't exist. We are working on that. There's an open ticket for that. We need to do that. The kernel itself provides that function. It's not exposed by Docker yet.
One of the use cases you were mentioning was multi-tenancy for Hadoop. What do you do about the HDFS file system and the fact that different tenants might be, is there a global file system or they each have their own?
In the way we are currently piloting this, we have separate HDFS file system per tenant. So we also have this is a little bit, and we haven't implemented all this yet, but it's possible to run a different HDFS file system that would be accounted as a remote file system. So basically, when it is integrated with Yarn, the integration applies to the node manager. And the data nodes can run on a different set of containers. Does that answer?
Yeah, roughly. I mean, I guess you need a scheduler that can schedule across the whole cluster or pool of resources, but then the container is only supposed to see its own data nodes and name nodes.
Right. So, yeah. If you're running a cluster, if you run the majority of all containers, then you would have a separate instance of HDFS per cluster.
Wondering if you have done any performance measurements of containers against VMs?
Containers don't have actually, well, there is some overhead, but it is not noticeable for general applications. Whereas for VMs, there is a lot of overhead, in particular for I/O, because I/O requires many more ASICs to access the devices. In fact, for compute, VMs are pretty efficient with all the changes that are made to the hardware, but I/O is still an issue. In the case of containers, there's almost no overhead.
So you're saying there's competition equivalent for compute on task?
So again,
Is there a claim that they're equivalent or compute-bound tasks?
Well, we did